The Earth's orbit and spin. Astronomy without a telescope. Copernicus is considered to be the founder of modern astronomy. He made his observations prior to the invention of the telescope and determined that the Earth rotated on its axis once daily and travelled around the Sun once every year. Whilst not a controversial topic today, this has not always been the case. Bruno, a supporter of Copernicus, was burnt at the stake by the Inquisition. Galileo was also brought before the Inquisition. There, under the threat of torture and death, was forced to renounce his beliefs in all Copernican theories. Galileo was then allowed to live out the remainder of his life under house arrest. Here the goal is to rediscover basic facts about the solar system, so let's get to it. First, let's consider the direction of the Earth's spin, ignoring for the moment its tilt axis. The Sun appears to rise in the east and set in the west, which is consistent with the Sun standing still and the Earth rotating from the west to the east, anti-clockwise if viewed from above the North Pole. Now let's look at the solar scope. Since you can't look directly at the Sun, I made what I call a solar scope. It is made out of standard PVC plumbing items, a length of 90mm stormwater pipe, 2 end caps and a Y junction. In one end cap I drilled a small hole. It is essentially a pinhole camera. Light enters the tube through the hole in one end of the cap and the image is formed on the other. The Y junction functions as a viewing port. Let's now have a look at the geometry of the solar scope. ds is the distance from the pinhole of the solar scope to the Sun. S is the diameter of the Sun. L is the length of the solar scope tube. And I is the size of the upside down image on the end cap of the solar scope. We essentially have two similar triangles. Triangles are said to be similar when corresponding angles are the same. One triangle, then, is a scaled version of the other. This means that ds divided by s equals L divided by I. This ratio is the distance from the Earth to the Sun in terms of Sun diameters. Dividing the length of the solar tube by the size of the image, we get our answer. In this slide, we're looking into the viewing port of the solar tube. We can clearly see the circular image of the Sun on the end cap picture plane. The image size is 2 centimetres. The length of the solar tube is 214 centimetres. So the length of the tube divided by the image size is 214 divided by 2, or 107. This means that the Sun is 107 Sun diameters away from the Earth. Next, let's determine the direction of orbit of the Earth. We have already determined that the Earth is rotating anti-clockwise when viewed from above the North Pole. Since the size of the Sun remains fairly constant from day to day, we know that either the Sun and the Earth are fixed, or that the Sun and Earth orbit each other. We're going to consider 3 scenarios. 1. The Earth, Sun and stars are fixed. 2. The Earth orbits the Sun with approximately the same direction of orbit as its spin. And 3. That the Earth's orbit is retrograde, that is, opposite to its spin. On the screen is a representation of the static model. Static means stationary or fixed, although we are allowing in this model the Earth to spin. The large yellow circle represents the Sun, the blue circle is the Earth, and the orange dot on the Earth is there to allow us to visualise the rotation of the Earth. The stars at the top of the screen represent those that are visible from the midnight position on the Earth. In the starting position, the orange dot is facing downwards. Initially, it also represents the midday position on the Earth as it is directly facing the Sun. After a single rotation of the orange dot, it is once again pointing directly at the Sun. A single rotation is exactly the same duration as that of a day. An observer looking up at the stars from the midnight position should see the same pattern of stars in the same location each and every night. Now let's consider scenario 2, where the orbit and spin are in the same direction. If you've ever looked out the window of a train or a car on a rural trip, you should have noticed that whilst the trees and other objects in the foreground seem to whiz past, those in the distance appear to follow you. What we're reacting to is the change in angle, and for distant objects the change in angle is unperceivable. Stars are among the most distant of all objects. In this animation, I'm going to move the stars with the planet to simulate this effect. The stars, however, are not actually moving, they're just an extremely long way away. In this, the initial position, the orange dot is both pointing downwards and directly towards the Sun. Let's look at that again. After a single rotation of the Earth, a person standing on the orange dot will not be looking at the Sun in the midday position. However, a person standing on the Earth on the opposite side to the orange dot will see the stars at exactly the same location as they were in the initial position, that is, directly above. If we rotate just a bit more till the orange dot is pointing at the Sun, we have the completion of one day. Note that a day is now longer than a single rotation. Now a person in the midnight position, that is, opposite to the orange dot, will observe the stars as though they had shifted to the west. Remember that the direction of the spin of the Earth is towards the east. Now let's look at scenario 3, with the spin retrograde to the orbit. That is, with an anti-clockwise spin as we watch the Earth orbit the Sun in a clockwise direction. We notice that the duration of a single rotation is now longer than that of a day. After a single rotation, a person standing opposite the orange dot would see the stars in the same locations that they were in the starting position of the day before. If we step back to the end of the first day, a person standing in the midnight position opposite the orange dot will find the stars rotated from their initial position to the east. Summary: the Earth's spin is towards the east, which is anti-clockwise when viewed from above the North Pole. The Earth's distance from the Sun is approximately 107 Sun diameters. In the fixed scenario, a day was the same duration as a single rotation, but in the second scenario, a day was longer than a single rotation, and in the third, a day was shorter than a full rotation. This is a simulation of what a person facing north will see if they look at the night sky at the same time and location on consecutive nights of a week. They'll notice that the stars move about 1 degree to the west when compared to the night before. As a guide, 1 degree is about the thickness of a finger held at arm's length. The change from night to night is subtle, but after a week is most definitely noticeable. Alternatively, we could have read the time when the night sky appeared the same as it was the night before. You should find that the pattern appears 4 minutes earlier each night. Once again, the time difference from night to night is small, but after a week it will accumulate to 28 minutes. By now you should have enough information to decide which scenario fits. So I'm not going to give you the answer. I'm going to let you determine that for yourself.